Hello everyone. In this lab, we are going to learn how we can model a 2D plate with elliptical hole and calculate the stress concentration factors. Here you can see a plate with length 400 millimeter, height 100 millimeter, and ellipse of dimensions 2.5 millimeter by 5 millimeter. And the material properties for this plate are also specified, which are 210 gigapascal and zero point 0.3 as the Poisson's ratio. We have the uniform thickness of 10 millimeter for this whole plate. What we need to do is to model 1/4 of a plate and calculate the stress along this line DD. Then we are required to find the maximum deformations and maximum stress along x, y, and z directions. And finally, what we need to do is to calculate the stress concentration factor for the plate by changing the value of h from 25 millimeter to 125 millimeter with 25 millimeters increment and find the stress concentration factor. Here, if we look at the graph, you can see that for our problem, we have B by A ratio, which is 0.5. So we are looking at this center curve. And in current scenario, when the dimension of H is 100 millimeter, 2A by H is 0.1. So the stress concentration factor is about 5 in this scenario. So we will change the value of H from 25 millimeter to 125 millimeter in the end. So let's shift to the answers for the analysis. We can move on with 2D analysis because the thickness is quite small as compared to other dimensions of the plate. I'll shift to ANSYS and we are going to use the static structure module. The first thing is to specify the material, and I'll just write the name mat here. So we have the name of the material that we want to assign, but since we haven't added any properties, we are seeing this small question mark on the left side of the material name. In order to perform the static structure analysis, we need at least two properties, which are the Young's modulus and Poisson's ratio, or maybe the shear modulus and Poisson's ratio. So any two of those will be enough. So the material is isotropic, meaning that the properties that we are assigning, they are same in all directions. So I'll just click on this isotropic elasticity and you will see we have this yellow color here where we need to specify the properties. The Young's modulus is 2 gigapascal, which will be 2E9, 210 gigapascals actually. Let me confirm this, 210 gigapascals, 210 E9, and finally the Poisson's ratio is 0.3. So when we specify the properties here, you can see that the question mark disappears, meaning that the material properties are defined correctly. I'll just close this engineering data. And before opening the geometry, since we are doing the 2D analysis, we have to change the analysis type under this properties tab of the geometry from 3D to 2D. So analysis type is 2D, and now I'm going to open the design modeler. So there are two ways we can model this plate. The first one is to model only the 1/4 section of the plate. It could be the right top, right bottom, or left top, left bottom section. Another way to model this problem is to first create this whole plate in the geometry and then specify the symmetry boundary conditions across two different planes, horizontal plane and vertical plane, and you will see that we will have only one quarter of the plate left after applying the symmetry. So I'll move on with the second method. And since the pressure is uniform, which is 10 megapascals, and the geometry is uniform, we can apply symmetry boundary conditions without compromising any real world features of this plate. So the easy way to model the plate is XY plane. I'll just go and sketch the rectangle. The next thing is to apply the constraints. I'm going to make this plate symmetric about vertical axis, and then I'll make the plate symmetric about the x-axis. Specifying the dimensions here. This is 400 millimeters. Oh, I'll need to change the dimensions. Just need to remember this. So this is 400 millimeter and this is 100 millimeter. I'll just focus a bit and move the dimension so that we have a complete view of the plate. So like this is good enough. Let me click on the move button here. Yeah, this is good enough. The next thing is to draw the ellipse. So we can simply use the ellipse feature in the draw tab and create the ellipse, the minor axis and the major axis, and specify the two dimensions. So the first one is this radius and the second one is this one. So we need to be very careful while specifying the dimension of the ellipse. So we have A equal to 5 millimeter and B equal to 2.5 millimeters. So these are the radiuses that we are talking about. So this one will be, let me check, 5 millimeter, and this one will be 2.5. Oh, sorry. Yes, this one will be 2.5 and this one will be 5. So we have this elliptical hole now with the required dimensions. And now I can convert this sketch using the concept feature surface from sketches. Simply selecting the sketch, apply, generate. So we have this plate now. Since we don't want to model the complete plate, I can specify the thickness here. Let me specify it first. That will be 10 millimeters. Okay. And what we can do is we can use the symmetry condition from the tools. So the plate is symmetric about, you see, the plate is symmetric about XY axis. Sorry, XZ axis. This is symmetric about XZ axis. Apply, generate. Now we only see the 1/2 portion of the plate. That we are going to analyze in the model. And plate is also symmetric about YZ axis. So we can repeat the process for YZ axis like this. So we have 1/4 model of the plate now, and I can close the geometry and move on with the model. So you see that when the model is open, we have the surface body 1/4 of a plate imported in the model for further analysis. Here we need to make sure that the behavior is set to plane stress and the material is set to the mat that we have defined previously. The next thing that you can notice is the symmetry here. You see we specified two symmetric planes and they are already present in the model. So these they have to be there. And I'm going to generate the mesh. So the mesh is not very good. So I'll just use the global control, changing the relevance to 100%, 100, and let's make this fine and regenerate the mesh so that we have a relatively good looking mesh. So this is quite better now. We will have stress concentrations near this hole. We may need to refine the stress around this region, but for now, I'll just move on with this specific mesh settings. The next thing is to specify the boundary condition. So we only have one boundary condition, which is the pressure that is 10 megapascals applied on the right side of the plate. So I'll right click on the structure, go to the pressure, select the region where I want to apply it, and select the direction here. So this is about 10 megapascals, so 10 E6. So the pressure is applied on the plate now, and what we need to find is, first of all, we need to find the stress distribution along the line DD. So what I'll do is I'm going to create a construction geometry, which will be the line or the path, and it will start from uh, the x coordinate. The starting point of the x coordinate will be 0, and coordinate will also be 0. However, y coordinate will start at, if we look at this, y coordinate will start at 5 millimeters. So this will be 5 millimeters. Let me change the units first. So it starts at 5 millimeter and it goes to the uh, 50 millimeters at the top. So this is the line along which we want to find the normal stress. So I'll insert the normal stress here and select the path along which I want to find and the direction of the stress. So I want to find the stress in x direction uh, that changes along this line y. So the next result that we need to look at is the maximum deformations and normal stresses along x, y, and z directions. So I'll just insert the deformation, directional deformation along x-axis. Just rename this. So we have x direction uh, deformation. I'll just duplicate this. We have y direction deformation. Duplicate this one again. And so yes, we are performing the 2D analysis. That's why we cannot find the deformation along z-axis. However, if we look at the stresses, let's say normal stress along x-axis, I'm going to duplicate this again, normal stress along y-axis, and duplicate this again, normal stress along z-axis. So we can find the stresses but not the deformations along all the axes, since we are using the 2D analysis. So the stress in the z direction, it only depends on so this is calculated based on the deformations in 2D plane actually. So we can rename this to z stress This is y stress and this is x stress. So we have the deformation, we have x, y, z, and now we can calculate for the results. We have the results here. You can see that the stress, how the stress varies as we move from as we move away from the elliptical hole. The maximum stress occur at this ellipse, which is about, let me change the units to something familiar. Yes, so we have the maximum stress of about 45 megapascals. The pressure that we have specified is 10 megapascal. So if we look at the deformation in x direction, so the maximum deformation is 0.009 millimeter, maximum deformation in z-axis. You see the maximum deformation is 0075 millimeter, and this is negative. The plate will be uh, contracting in y region. Since we are extending in x region, it will be contracted in y region. So this is the stress in x direction, stress in y direction, and there are very minute differences, and the stress in z direction, which will be zero because we are solving for the plane stress problem. However, if we want to look at the strain in z direction, so I'll just evaluate the result, you will see that it will not be zero. So the strain in z direction, it does exist because of the stresses in x and y directions. Let's move on with calculating the stress concentration factor. So for that, we have the maximum stress, which is 45.455 megapascal. And if I go back here to the graph, we can see that the stress concentration factor in this case is simply the maximum stress divided by the applied stress. So if we divide 45 with 10, we will get 4.5 as the stress concentration factor, which will be around here, and it is less than the one that is in the theory. So we can calculate the error that is generated due to FEA. Also, these equations, they are for actually the infinite uh, plate. So these equations, they are for plate with infinite length. So that's why we are getting the small error. Let's change the geometry. So for now, we have used H as 100 millimeter. Let me change this to 25 millimeter and see what happens to the maximum stress. So I will simply go to geometry, and in the geometry, we can select the sketch and change the dimension to 25 millimeter here. You will see that the rest of the things, they are updated automatically. I'll just minimize this maybe and update the data in the model. So update upstream components. So we have this new plate that is in the model, and I'll simply run the analysis. The maximum stress increases from 45 megapascal to 55 megapascal. We used H to be 25, so 2A divided by H will be equal to, let me check. So 10 divided by 25, that will be 0.4. And at 0.4, if we go here, the stress, it is just above 5.5. So you see that we have the maximum stress 5.5, the pressure is 10, so the stress concentration factor in this case will be 5.5. So this is how you can plot the stress concentration factors by changing the geometry. That's all about this current lab. Thank you so much for your time, and we will back with the next lab soon.